Hello everyone, this is Ranjith Kolakkattil. Title of my presentation is Influence of Edge Valencies on the Overall Resistance of Single or Reticulated Cylindrical Cells. Like any other design software, the designer should configuration possible in few clicks. All you have to do is just give the dimension of the space and the loading. And the best possible shell configuration is obtained based on parameters such as valency, dimensionality, extent. This is where this study become important. Today we will see how few of these parameters influence the constants. First of all, let's go through a small introduction on parameters of the configuration. Cylindrical shells are used when the length is much greater than the span of the space to be covered, like relay station platforms. Parameterization principles can be utilized in creation of different shell configurations. Coming to the parameterization of a structure. Structure can be defined as a unit of elements, vertices, edges, faces, and cells. In order to interrelate these elements in a structure's parameters as been defined, they are dimensionality, valency, and extent. Valency is the prime focus for this present study. Valency is defined as a number of elements of a given dimensionality that's connected to the elements of another dimensionality. There are different dimensionality. There are different valencies for a structure, out of which V1, that is the edge valency of the vertex, and F1 edge valency of face, that are the primary concern for this present study. Their influence on the load capacity of single shells are studied here. So the edge valencies within a structure can change. So these are the examples for configuration where edge valencies changes within a structure. So there arises a need for average edge valencies. So average edge valences are defined based on these equations. Coming to the objective of the study, three shell configurations with the different edge valencies of faces and edge valencies of vertices are selected for this study. The three configurations are subjected to linear eigenvalue buckling analysis and geometrical and material nonlinear analysis. As a result, the relation between the load capacity and the average edge valences are studied. Within a shell itself, the right-to-span ratio is varied. Right-to-span ratio of 1 is to 10, 1 is to 8, and 1 is to 6 are considered here. To the linear eigenvalue buckling analysis. First buckling mode, shells under uniformly distributed load is given here. All these shells have similar buckling modes, hence first mode shape is independent of the average edge value. To the buckling load factor. As the weight of the three configurations are different, a new parameter is introduced for comparison of buckling load factor. The parameter is defined by dividing with the total weight of the structure. The graph shows the variation of the load factor of different rise-to-span ratios of the configuration. The figure shows that the buckling load factor increases as the rise of the shell increases for all the three configurations. Moving to the variation of buckling load parameter with the average edge balances. The load factor parameter increases and decreases as the average edge valency of the shell increases. A second degree polar curve is fitted to observe this variation. Since linear eigenvalue buckling analysis cannot capture the actual behavior of structure, geometrical and material nonlinear analysis is conducted in the second stage. Difflected shape of shells are given here. As the total weight of the shells are slightly different, a new parameter is introduced similar to the eigenvalue buckling analysis. So based on this new parameter, the variation of load factor with the cement to rise ratio is plotted here. As the cement to rise ratio increases, the load factor also increases for all the three configurations. Using the same parameter, the effect of variation in the average edge valency is measured, and the results are provided in these graphs. And second degree polynomials will be in this in order to understand general trend. Similar to eigenvalue buckling analysis, the load capacity increases, then decreases as the average edge valency of the vertices and average edge valency of the faces increases. While analyzing the failure pattern, few observations are made. The configuration on the extreme left side, the failure tend to be at the edges where the average edge valencies of vertices is less. For the configuration on the right side, where the failure happened at the center, where edge valency of the faces is high. For the configuration on the center, the failure happened to be at the ground region, where F1 is same, but V1 is great later at the interior. So let's look at the results obtained from this study. Linear elastic buckling mode is independent of the average edge valency of vertices and faces. High average edge valency of vertices or low average edge valency of faces does not guarantee high load capacity of the shells. And from the graphs, we can see that high load capacity increases initially, then decreases with average edge balances. And finally, the V4 configuration have higher load capacity among the three configuration under equal weight of the structure. This study have few limitations. So the present study only considered uniformly distributed load, which may not be sufficient. And the results are applicable to only the given tree-shell configuration with the selected parameters. And there is a non-uniformity among number of vertices, number of edges, and number of faces. So which might have contributed to this results, as the number of vertices, number of edges, and number of faces are different, and the length of the members are also different, and the centeredness ratio of the members are so different, which may contribute to the load capacity of these shells. And finally, there is an exclusion of stiffness of the member and the orientation of the members. Incline orientation of members are actually not considered in the present study. So to summarize, the effect of edge balance on the strength of the reticular shells has been captured by eigenvalue buckling analysis and the geometrical and material nonlinear analysis. The overall resistance of cylindrical shells actually increases initially, then decreases with the average edge valency of the vertices and faces. Edge valency of the vertices with the low magnitude or the high magnitude of average edge valency of faces can initiate the failures for a single reticulated shells. So these are the key findings from this study. Thank you for listening.